So welcome everybody. I have the honor and above all the great pleasure to chair today's talk in the series, the seminar in the analysis and methods of PDEs. So today's speaker is Professor Monica Visan. She's a very well known, but the tradition imposes 1 minute of recollection of her successes and her career. So Monica Visan is currently professor at UCLA, which was the place where she got her PhD. After that, she spent 2 years at the Institute in Princeton. Then she went to Chicago. She spent some time in Austin. And then finally, she came back to UCLA, where she is now. So she got many distinctions, Clay Fellowship, Harrington Fellowship, Sloan Research Fellowship, and so on. But also, she received 3 years ago the Sorgenfrey Distinguished Teaching Award. So she is not only an excellent researcher, but also a very good teacher. This is good. So her main field of expertise, I think I can safely say that she's an expert, world-class expert in nonlinear Schrödinger equation, but also on other dispersive equations and integrable systems, and of course, harmonic analysis. She has given many important contributions. Maybe I just mention a couple. First of all, at the start of her career, the solution of the remaining problem on the well-posedness for the energy critical, the focusing nonlinear Schrödinger equation in high dimension, which is by now a classic result, a classic group of results in the theory. And maybe also mention the joint work on the well-posedness for KdV on the line in H-1, and many other important results. Okay, today's talk will be on the more recent field of study, determinants, commuting, flows, and recent progress on completely integrable systems. So, Monica, it's up to you.
All right, thank you very much. Thank you for the very generous introduction. So let me start by introducing the protagonists in today's story and briefly review their well-posedness history. So I selected here 3 equations that are very well known and that have been intensively studied. We have the Korteweg-de Vries equation. We have the one-dimensional cubic nonlinear Schrödinger equation. As you see, it comes in 2 flavors, defocusing or focusing, depending on the sign in front of the nonlinearity. And we have the Hirota modified Korteweg-de Vries equation, namely the model for complex valued solutions. Now, if you're interested in the real valued Miura MKDV equation, it's enough to study this model over here for real valued initial data, because the realness of the values is preserved by this flow, okay? Now, for each one of these equations, I have a thermometer that gauges the well-posedness of these equations in L2 base Sobolev spaces at regularity S. Okay. Now, when I say well-posedness, I mean well-posedness a la Hadamard. Okay. So, in particular, if I say that the equation is globally well-posed, I mean that the solutions exist for all time. They are unique and they depend continuously not only on time but also on the initial data. Now, in all 3 cases, this purple region over here is a region of well-posedness. So, for the KdV equation, this was proved by Molinet. Specifically, he showed that the data to solution map fails to extend continuously in HS as soon as S is less than -1. Okay. Now, for the nonlinear Schrödinger equation and the MKDV equation, we actually have norm inflation in HS as soon as S is smaller or equal than -0.5. And this was proved, for example, by Chris, Colliander, and Tao. By norm inflation, I mean that arbitrarily small initial data can become arbitrarily large, arbitrarily quickly, okay? Now, the green region on these thermometers over here is a region of analytic well-posedness. This is basically what can be achieved by contraction mapping arguments. And when I say contraction mapping, this is not to be taken lightly. Okay, it relies on ever more sophisticated harmonic analysis tools for proving both linear and nonlinear estimates. For example, global well-posedness for KdV in L2, namely when S is equal to 0, was proved by Bourgain using the newly introduced XSB spaces. Local well-posedness for S bigger than -3/4 was proved by Kenny, Pons, and Vega. Global well-posedness for S bigger than -3/4 was proved by Colliander, Kill, Statilani, Takao, Kantao using the almost conservation laws argument. Global well-posedness at this threshold, -3/4, was obtained independently by Guo and Kishimoto. Now, no matter how good your harmonic analysis is, the green region is the limit of what can be achieved by contraction mapping argument. And we know this because there is a mild form of ill-posedness that was also proved by Chris, Colliander, and Tao that says that the data to solution map fails to be uniformly continuous below the green region over here. Now we know that in the purple region, we have failure. I'm sorry, this thing is moving with me. We have failure of failure of continuity of the data to solution map. So that leaves us with this red region over here, where well-posedness is still possible, though the data to solution map will no longer be analytic. Okay. Now, the reason why this mild form of ill-posedness is important is because it rules out a wide range of proof techniques. Okay, it basically tells you that you can no longer treat the nonlinearity over here as a perturbation of the underlying linear flow. Okay. Now, for the nonlinear Schrödinger equation, well-posedness, global well-posedness in L2 was proved by Tsutsumi, who used Strickard's estimates in his contraction mapping argument. This was about 35 years ago. And since then, no progress has been made on the well-posedness problem for the nonlinear Schrödinger equation in L2 base Sobolev spaces since then, okay? Now, for the MKDV equation, local well-posedness in H1/4 was proved by Kenny, Pons, and Vega. Global well-posedness for S bigger than 1/4 by Colliander, Kill, Statilani, Takao, Kantao, and global well-posedness at the threshold, again, by Guo and Kishimoto independently. Now, also for NLS and for the MKDV equation, we have the presence of the red region, where we also have this failure of uniform continuity of the data to solution map. Okay. However, well-posedness could still be possible. Okay, so this leaves us exactly with this red region over here for these three models. And this is the subject of recent joint work with Rowan Killev and Ben Harrop Griffiths and Rowan Killev. And it's what I want to talk to you about today. Okay, it turns out that the red region is also a region of well-posedness, though the data to solution map will only be continuous and not analytic, like in the green region. Okay, now, one thing that all these three equations have in common is that they are completely integral. And it seems that the presence of this red region over here is a feature of this completely integrable system. So let me explain. All these equations over here can be considered particular cases of more general equations. For example, replacing the nonlinearity over here by the spatial derivative of q to the k, where k is now an integer big or equal than 2, one obtains the generalized Korteweg-de Vries equation. If k is equal to 2, this corresponds exactly to the KdV. If k is equal to 3, this corresponds to the real valued MKdV equation. Now, similarly, one can replace the nonlinearity in the Schrödinger equation by, let's say, q to the power 2k times q, where k now is an integer big or equal than 1. For k is equal to 1, this is precisely the cubic NLS. Now, it turns out that in all non-integrable generalizations of these equations over here, the threshold at which analytic well-posedness fails coincides with the threshold at which ill-posedness starts. Okay, so it is precisely for these completely integrable equations that we need new methods in order to attack the well-posedness equation in the red region. Okay, one needs to develop non-perturbative methods in order to answer the well-posedness question in this region. All right. Now, the KdV equation has an illustrious history as a completely integrable system. It is, after all, the first nonlinear PDE discovered to be completely integral. And that is thanks to work by Gardner, Green, Kruskal, and Jura, who were physicists at the Princeton Plasma Physics Laboratory. Now, among the many remarkable discoveries about the KdV equation is the fact that the KdV equation admits infinitely many conservation laws. And I wrote down here the very first three. The first one corresponds to the conservation of matter. The second one corresponds to the conservation of momentum. And the third one corresponds to the conservation of Hamiltonian. All right, now it's enough to look at the first density that appears over here, or the second term in the third density, to see that these densities over here are not necessarily sign definite, right? Which means that these conservation laws are not necessarily coercive. Nevertheless, one of the important contributions of Peter Lax to the theory of KdV was to observe that if one combines carefully finitely many conservation laws, then one can restore coercivity. Okay, specifically, one can control the solution at time t in L2 base Sobolev spaces with integer number of derivatives uniformly in time in terms of the corresponding norm of the initial data. Okay. Now, if we want to make progress on the red region over here, in particular, if we want to prove global well-posedness in H-1 for the KdV equation, we need to go in the opposite direction over here. We need a priori bounds in low regularity spaces. If you think about it, the triumph of Colliander, Stafilani, Takaoka, and Tao was exactly that, right? By modifying these polynomial conservation laws of Gardner, Green, Kruskal, and Jura, they proved that they are almost conserved, and that gave them access to bounds, a priori bounds on the low regularity norms that allow them to continue the solution globally in time. Now, the a priori bounds that I would like to describe to you today were obtained in joint work with Rowan Keller and Xiaoyi Zhang. And they say the following thing: short solutions to the KdV equation satisfy the following bounds. One can control the solution in HS uniformly in time in terms of a function of the initial data in the same space HS. Now, I wrote here an exponential for simplicity. In fact, what one gets is a polynomial of degree that depends on S. And I wrote down here S between -1 and 1, just so that I can capture the red region, though the methods extend to cover all remaining values of S as well. Now, for the nonlinear Schrödinger equation and the modified KdV equation, we have a similar bound where one can control the solution in HS uniformly in time in terms of the initial data in the same space, again, throughout the red regions. Okay. Now, because all these equations enjoy time translation symmetry, one can use that in order to also obtain lower bounds on the HS norm of the solution at time t in terms of the initial data. Okay, so this basically tells us that the HS norm of the solution at time t is comparable to the HS norm of the initial data, which basically says that the HS norm is essentially conserved. Okay, now I stated this theorem over here for Schwartz solutions in order to emphasize that this is not a low regularity problem, right? It is a problem about conservation laws, even for nice solutions to these equations. All right, so a bit of history. A priori bounds in H-1 for the KdV equation have been obtained before. There are proofs due to Ripken, to Buchmaster and Koch, and also Koch and Totaro. Also for the nonlinear Schrödinger and MKdV equation, there is a competing approach due to Koch and Totaro. Now, the advantage of the method that I would like to describe to you is that it is very robust, okay? It works uniformly for this equation posed on the real line, as well as for their periodic analogs. It also applies to other completely integrable equations. In fact, it has been successfully employed in the context of the Benjamin-Ono and the derivative nonlinear Schrödinger equation. Okay, so what is that method? Well, I am going to describe it in the context of the Korteweg-de Vries equation, because I believe that that system, well, that setting is somehow the cleanest, and the objects that we are going to encounter are the most familiar. Okay, so in order to prove these a priori bounds, we are going to rely on the Lux pair formulation for KdV. Okay, so what is that? Well, here is the Lux operator. It's a time-dependent operator, which is a Schrödinger operator, where the potential, excuse me, is given by the solution to the KdV equation at time t. And here is the Peter operator. It is an anti-self-adjoint operator. Then the observation of Peter Lange is that Q solves the KdV equation if and only if the time derivative of L is the commutator of P with L. So let me take 1 minute to explain a consequence of this formulation over here. So let's take U to be the solution to this initial value problem over here. Okay, then because P is anti-self-adjoint, U is going to be unitary. And one can check that L at time t is L at time 0 conjugated by these unitary operators over here. What does that mean? Well, let's imagine for a second that all these objects that we are encountering are nice finite dimensional matrices, okay? Then a relation like this would immediately tell us that the characteristic polynomial of L at time t is equal to the characteristic polynomial of L at time 0. So that means that the eigenvalues of L at time t are the eigenvalues of L at time 0. That means that the eigenvalues are left invariant by the KdV flow. Okay, now we are going to generalize this from the case of finite dimensional matrices to infer that all spectral properties of L are conserved. Our goal is not to make sense of this statement over here for our rough, slow decaying potentials, but rather to use it as a guiding principle to define the right objects to study. Okay, so our goal is to connect norms of Q, in particular the H-1 norm of Q, to spectral properties of this operator. Because since we believe that the spectral properties of L are left invariant by the flow, this would tell us that the H-1 norm of Q is going to be left invariant by the flow, and hence give us our essential conservation law. Okay, so how are we going to do this? Well, generalizing from the case of finite dimensional matrices, it is natural to try to look at the polynomial, the characteristic polynomial of the operator L at this spectral parameter k squared, right? So you simply take the determinant of this object. Now, the problem is that this object over here doesn't make any sense, even if Q is identically equal to 0, right? I mean, for example, on the torus, what would it be? The determinant is the product of the eigenvalues. You get an infinite product that doesn't converge in any sense, right? So at the very least, one needs to normalize it by the characteristic polynomial of the free Lux operator, where this potential over here is taken to be equal to 0, okay? And after simplifying, we write it like this. Now I have to explain to you what do I mean by this notation, right? And what I mean is the composition of Q with the resolvent of this operator over here. Now one can take that resolvent and one can put it to the left of Q, or one can put it to the right of Q. But the problem is that in either case, these operators over here are only bounded on L2 if Q is locally in L2, okay? Now, that is perfectly fine for a Schwartz potential, but ultimately at the back of our mind is that we want to extend these a priori bounds using a well-posedness theory to all potentials in H-1. So having things depend on the local L2 norm of a potential is simply unacceptable, okay? We want all our objects to only depend on the H-1 norm of Q. Now, it turns out that one can resolve the low regularity problem by taking half of the resolvent and putting it on the left, and taking the other half and putting it on the right. I'm going to explain this on the next page. Okay. So in this way, we are led to this object A, right, which is the perturbation determinant. Now, this is actually a very well-studied object, at least for Schwartz potentials Q. And a good reference for this is a paper by Deift and Trubowitz. For example, for Schwartz potentials Q, it is known that this perturbation determinant is a holomorphic function in the upper half plane, that it extends continuously to the real axis. It is known that it has finitely many zeros in the upper half plane, all of them simple, all of them located on the imaginary axis. And it converges to 1 at infinity uniformly in the closed upper half plane. Okay. So what is the problem? Well, the problem is that this Fredholm determinant over here converges if and only if this operator over here is trace class. And that introduces a new issue. It's not a low regularity issue, it's a slow decay issue, right? One can actually write down what is the trace of this operator explicitly. It's written over here. So we see that up to some factors, it's basically given by the integral of Q. Now, again, this is not a problem for Schwartz functions, but it is a problem for our potentials. We want to treat potentials that are like L2 at infinity, not like L1 at infinity. So this is simply unacceptable. Okay. So how are we going to modify this object over here in order to deal with our slowly decaying potentials? The answer is actually a renormalization that goes back to Hilbert. So what one does is we take this Fredholm determinant that appears over here, and we multiply it by the exponential of minus the trace. This is known as the det2 object. And the advantage is that the definition of this object over here extends from trace class to Hilbert-Schmidt operators. And this line over here justifies that. Let's see. So again, what is the determinant? Is the product of the eigenvalues. What is the trace? Is the sum of the eigenvalues. Let's take a logarithm in order to turn that product into a sum. Okay, and now let's expand this logarithm over here into a power series in lambda. We'll do a Fubini to sum first in the eigenvalues, and what we end up with is a geometric series in A. Now, this geometric series over here converges as soon as the dominant term, which is the term corresponding to L equals 2, is sufficiently small. Now, the term corresponding to L equals 2 is exactly the Hilbert-Schmidt norm of A squared. Okay, so this series over here converges if, for example, the Hilbert-Schmidt norm is less than 1, right? To control the remaining terms in the series, one can use the nonlinear Hilbert inequality in Schatten class. Okay, so based on these considerations over here, one is led to consider the renormalized perturbation determinant. So this is the det2 object corresponding to this operator. And for our analysis, it is convenient to actually work with the logarithm of this object, which is alpha, right? Note that we are restricting the renormalized perturbation determinant to the imaginary axis in order to define the alpha. And per our discussion above, it is now a geometric series in Q, okay? Now, this series over here converges as soon as the operator that appears over here has a Hilbert-Schmidt norm that is sufficiently small. What is the Hilbert-Schmidt norm of this operator? Well, here it is. One can actually write it down explicitly. So up to factors of kappa, it is exactly the H-1 norm of Q, okay? And one can make this term over here small simply by taking kappa to be sufficiently large, the depending on the H-1 norm of Q, okay? Now, a convergent geometric series is as large as its dominant term. So that means that this alpha over here is proportional to the H-1 norm of Q, okay? So if I want to prove that the h-1 norm of Q at time t is proportional to the h-1 norm of Q at time 0, all I have to do is prove that this object over here is left invariant by the KdV flow. Okay, and that is exactly what we do in the paper with Rowan, Kilep, and Shaoyi-Zhang. We simply take a time derivative of this object over here, and we prove that that is equal to 0. Okay, so this gives us a way of comparing the h-1 norm of the solution at time t to the h-1 norm of the solution at time 0. And so we obtain that Schwartz solutions are uniformly bounded in h-1. Now, an advantage of this method over here is that it actually tells us more than just a priori bounds. It tells us that the orbits are actually equicontinuous in h-1. So let me explain. Okay? So what do we know? We know that because of conservation of alpha, this object over here on the right-hand side is proportional to the h-1 norm of the initial data. Okay? The initial data is just one function. Okay, so taking kappa to be really, really large, depending on the h-1 norm of thus one function, we can make this object over here as small as we want to. Okay. So that means that we can make this object that now depends on time, we can make it as small as we want to by taking kappa to be really, really large. And we can do this uniformly in the time parameter. But this object over here controls the contribution of frequencies bigger than kappa to the h-1 norm, right? Because xi is being bigger than kappa means that xi squared dominates this kappa squared. So what did we recover? We see that we can make the contribution of the high frequencies arbitrarily small, uniformly in time, by taking kappa to be really, really large. So that means that the orbit of the KdV equation is tight on the Fourier side. There is very little norm at the Fourier infinity. And tightness on the Fourier side corresponds by Plancherel to equicontinuity on the physical side. Okay. So this is how we obtain that the orbits of short solutions are not only uniformly bounded, but they are also equicontinuous in h-1. And this is going to be an important ingredient in our well-posedness story. Okay. But before we go to the well-posedness story, I want to take just a very quick detour to discuss one of the applications of the conservation laws to orbital stability. Okay. So in fact, one of the first applications of the polynomial conservation laws discovered by Garner, Green, Kruskal, and Miura has been to prove that certain solutions to the KdV equation, for example, these solitary wave solutions that I have written over here, are orbitally stable. By orbitally stable, I mean that if you start close to a solitary wave solution at the initial time, then the solution will remain close to a solitary wave solution. Now, let's look over here at this formula for a solitary wave solution. It has two parameters. One is a positive parameter beta, and the other one is a real parameter c. By inspecting this formula over here, we see that the solitary wave solutions move to the right. Their velocity is proportional to beta squared, as is their amplitude. They are localized at the spatial scale 1 over beta, and at time t equals 0, they are localized around this center C. Okay. Now, in pioneering work, Benjamin proved that these solitary wave solutions are orbitally stable in H1. And he did this by proving that these solitary wave solutions are local minimizers of the energy functional subject to constrained momentum. Now, his proof had some mathematical gaps that are later filled in by Bona, but nevertheless, these two works over here are exceptional, okay? They predate by about 2 decades the proof that the KdV equation is actually globally well-posed in H1, okay? This was achieved in the early 90s by Koenig, Pons, and Vega. Nowadays, the term solitary wave has been supplanted by the term soliton. Okay, now this was introduced by Kruskal and Zabusky in a paper where they were doing numerical observations of the KDE equation. And they remarked that solitary wave solutions have particle-like interactions, hence the name soliton. Okay, so for example, they noticed that two solitary waves would collide, they would interact non-linearly for a while, and then they would reappear. Okay, now in the words of Kruskal and Zabusky, they pass through one another without losing their identity. Okay, now of course, if you look at the trajectory of one of these solitary waves, it is not a straight line. There is a shift that is caused by the interaction. However, the amplitude and the velocity with which the solitary waves emerged from the interaction was the same as the amplitude and the velocity with which they entered the interaction. By generalizing the work of Benjamin, Maddox and Sachs proved that n soliton solutions are orbitally stable in Hn. Okay, so again, they did this by proving that n solitons are local minimizers of the n+1 conserved quantity subject to constraining the first n conservation laws. And from this enumeration over here, we are throwing away matter. Matter is the number 0 conservation law. I should also mention here additional results on orbital stability that use the global well-posedness of this equation in H1 and also in L2. Okay, so Merle and Vega proved that single solitons, these objects over here, are orbitally stable in H1. Martel, Merle, and Tsai proved that n solitons are orbitally stable in H1. And adapting their argument to the Gardner equation, Alejo, Munoz, and Vega proved that n solitons are orbitally stable in L2. Now, it is natural to ask, given that we discovered these additional conservation laws at a lower regularity, can we say something more about the orbital stability of this equation? Okay, of these multisolitons? Can we, for example, prove orbital stability of n solitons in H-1? Even more, can we find a variational characterization of multisolitons that still makes sense in H-1 and not just in Hn? Okay, and the answer to both those questions is yes. So here is a theorem that we proved with Rowe and Keller. It says the following thing. Let's fix n to be bigger or equal than 1, and let's fix n distinct positive parameters. They encode the velocities of the soliton. Then for every epsilon bigger than 0, there is a delta, such that if the initial data starts within delta from the manifold of multisolitons with parameters beta, then the solution forevermore is going to remain within epsilon from that manifold. Okay, and there are two remarks I want to make over here. The first one is that we can take this delta to be uniform over the manifold of multisolitons. It does not depend on the particular parameters of the multisoliton you started close to. And secondly, using the conservation laws, either the polynomial ones or the ones that I discussed before, one can extend the result to state orbital stability in Hs for any s bigger than -1, right? It is a consequence of orbital stability in H-1 that we obtain orbital stability for all remaining spaces as well. And the fact that this parameter delta over here can be taken to be uniform in the manifold is a new result even in H1. Okay. All right. Now, what about the second question? Can we come up with a variational characterization of multisolitons that makes sense at low regularity? The answer is yes. Here it is. Again, we fix n to be bigger or equal than 1. We fix these parameters betas to be positive and distinct. Now, if you start with a potential that has the following property, the renormalized perturbation determinant has these zeros on the imaginary axis, the one given by the parameters beta. then the renormalized perturbation determinant is going to be bounded by the renormalized perturbation determinant corresponding to a multisoliton with those parameters beta. Okay. Moreover, if equality holds for one kappa in this relation over here, then it's going to hold for all kappa, and Q will necessarily be a multisoliton. Okay. So to paraphrase what this thing over here says, is that multisolitons are the unique global maximizers of the renormalized perturbation determinant subject to constrained zeros on these imaginary axes. Okay. All right, so that's my detour into orbital stability and applications to the conservation laws. Let's go back to the question of well-posedness in the red region. Okay, so what did we achieve so far for the KdV equation? And also for NLS and MKdV. We proved that the solutions satisfy a priori bounds in the red region, and also that the orbits are equicontinuous. Okay. Now, a priori bounds are great, but they are not enough in order to prove well-posedness, right? If you think about it, conservation of L2 was actually known to Korteweg and De Vries, but we had to wait for Bourgain to show us how to construct global dynamics for L2 initial data, okay? In order to prove well-posedness, what we really need to do is control the difference of two solutions, okay? Now, complete integrability tells us a lot about the orbit of a single solution, but it doesn't tell us much about the differences of solutions. So in order to deal with this issue, we introduced what we call the commuting flows argument. So let me explain what that is. Now, it is well known that for Schwarz potentials, if one takes this object alpha, which is the logarithm of the renormalized perturbation determinant, and expands it into a power series in 1 over kappa, then the polynomial conservation laws of Gardner, Green, Kruskal, and Miura appear in sequence as coefficients. Okay, so here's what we do. We ignore these lower order terms for a second, and we solve for this term. Okay, so this leads us to define these H kappa Hamiltonians that you see as kappa goes to infinity, better and better approximate the KdV Hamiltonian. So formally, at least, we expect that the H kappa flow is going to be a good approximation to the KdV flow as kappa goes to infinity. Now, the KdV flow conserves momentum, and we saw that it conserves alpha. Okay, so it's going to conserve the H kappa Hamiltonian. In fact, it turns out that all these Hamiltonians that I wrote over here Poisson commute with each other. Okay, so what is this H kappa flow? Well, one can simply write it down using the symplectic form. So what is it? It's essentially a transport equation where the forcing term is given by the derivative of G. I never told you what G is. G is the diagonal Green's function of the Lax operator with potential Q. Okay, now because one can write down the resolvent series, one sees that this function G over here is actually an analytic function of Q. And because of the resolvent, it gains 2 degrees of regularity compared to Q. So if Q is in H-1, then this G object is actually in H1, and it depends analytically on Q. So one can actually treat the well-posedness problem for this equation over here using ODE methods, okay? So one can easily prove that this H kappa flow over here is locally well-posed in H-1. Now, how do I extend local well-posedness to global well-posedness? I need a priori bounds. But because this H kappa Hamiltonian commutes with alpha, the H kappa flow leaves alpha invariant, okay? So since alpha, as we saw, encodes the H-1 norm, this says that this flow over here satisfies a priori H-1 bounds, Okay, so local well-posedness plus these a priori bounds allow us to construct global dynamics for the H kappa flow. Moreover, since alpha also encodes equicontinuity, as we saw, the orbits under the H kappa flow are also equicontinuous in H minus 1. Okay, so here's the picture. What are we trying to do? We are trying to prove that if you start with two initial data that are close, then the corresponding solutions at time t under the KdV flow are also going to be close. Okay. Now, the advantage of working with commuting flows is the following. To flow for time t under the KdV flow is the same as flowing for time t under the H kappa flow, and then flowing for time t under the difference of the Hamiltonian. Now, since we saw that the H kappa flow over here is well posed in H minus 1, if we start with initial data that are close, then the solution at time t under the H kappa flow are going to be close. So by the triangle inequality, if I want to prove that these solutions over here are close, it's enough to prove that these arrows are short. Okay. In other words, I want to prove that the evolution under this difference of the Hamiltonians converges to the identity as kappa goes to infinity. Okay, so here's the goal. Here's my initial data. This is just notation for the evolution of that initial data at time t under the difference of the Hamiltonians. And I need to prove that on some compact time interval, this converges to 0 as kappa goes to infinity in H minus 1. Okay. Now, there is a caveat over here. I have to do this uniformly over equicontinuous families. Why? Well, what is this initial data that I want to prove this statement for? It is precisely the solution at time t under the H kappa flow. And all I know about the solution at time t under the H kappa flow is that the orbit is uniformly bounded and equicontinuous in H minus 1. So it behooves us to prove this statement uniformly over equicontinuous families in H minus 1. Okay, so have we made progress, right? Let's stop a second and think. What have we achieved so far? We have to understand the KdV equation in H minus 1, and that seems to be hard. And we are approximating it by a flow, the H kappa flow, which we saw was easily seen to be well posed in H minus 1. And we want to prove that whatever is left over converges to the identity, okay? So this seems non-trivial, right? Because the evolution, the high frequency portion under this evolution still evolves according to the KdV flow. So what progress have I made, if any? Well, the progress lies in the fact that I no longer have to control differences of solutions. I simply have to understand the evolution of a single initial data, albeit over equicontinuous families. Okay, so this is where the progress was made. So how do we prove such a statement? Well, it is tempting to change variables, right? Nobody likes to work at low regularity. So how are you going to find a smart change of variables? Well, we're going to go to the diagonal Green's function. We saw it's a nice analytic function of Q that gains 2 degrees of regularity. So restating everything in terms of this new change of variables, we now have to prove convergence in H1 to 0. What is G at 0 is the diagonal Green's function corresponding to this initial data. What is G at t is the diagonal Green's function corresponding to this solution at time t. Now, how do I compare the evolution at time t to some initial data? By the fundamental theorem of calculus, it's enough to control its time derivative. So here is the time derivative under the difference flow, and it is what it is. The only term that I want you to look at is this one. Okay, so we want to handle H minus 1 potentials, and we are taking a derivative. Okay, so that means that if I am to have any sort of success in proving this convergence to 0, I can only do it in H minus 2. And with a little bit of work, that can be done. Okay, so we have convergence in H minus 2. but we wanted convergence in H1. So we are 3 derivatives away from our goal. Okay, how are we going to make up for this loss of derivatives? And the answer is equicontinuity. Okay, so first of all, because our change of variable is a nice diffeomorphism that commutes with spatial translations, it maps H-1 equicontinuous families to H1 equicontinuous families. So now we use a well-known fact in harmonic analysis. If we have a sequence that converges in a low regularity space and it's equicontinuous in a high regularity space, then it actually converges in the high regularity space. And the reason why is because equicontinuity means that one can ignore the high frequencies, right? High frequencies are small anyway. So one only needs to prove convergence of the low frequencies. But the low frequencies don't really care if you are in a high regularity space or a low regularity space. So the convergence from the low regularity space is going to imply convergence of the low frequencies in the high regularity space. And this is how we upgrade equicontinuity to convergence. And that's exactly what we have here. We have equicontinuity in a high regularity space, and we have convergence in a low regularity space. And this implies convergence in the high regularity space, H1. Okay, so this is how we reach our goal. So putting everything together, this is the theorem that we proved with Rowan. The KdV equation is globally well-posed in H-1. So the statement is that the data to solution map extends uniquely from short space to a jointly continuous map of time and initial data with values in H-1. And for each initial data, the orbit of the corresponding solution is uniformly bounded and equicontinuous in H-1. Now, using this equicontinuity over here, a consequence of this theorem is global well-posedness for the KdV equation in the remaining red region as well. Okay. All right. So now, if you remember, at the beginning of the talk, I listed 3 equations. So it's natural to ask, does the argument that I just described also allow us to prove well-posedness for the NLS and the MKDV equation throughout the red region? And the answer is no. Okay. Now, I didn't give you enough details. Okay. But if I had, you would have noticed that our argument for obtaining a priori bounds and for deriving well-posedness did not rely on the geometry of the underlying space, right, the real line. It actually works equally well for the periodic KdV equation. Now, it is well known that the periodic nonlinear Schrödinger equation and the periodic MKdV equation is ill-posed below L2. And indeed, if you just repeat the arguments that I described in the context of NLS and MKDV, then one obtains well-posedness for these equations all the way down to L2, both on the real line and on the torus, okay? And for the periodic setting, this is known to be sharp. So if you want to make progress on these equations throughout the red region below L2, then one needs to start distinguishing between the 2 geometries. And our answer to that was the local smoothing effect. So let me explain that for a second. So what is local smoothing? When the principle that underlines the local smoothing effect is the fact that the high frequency portions of the solutions move sufficiently fast to evacuate any compact region of spacetime. And what is left behind is this low frequency portion of the solution, which is smoother. In fact, the first local smoothing effect was obtained by Kato for the Korteweg-de Vries equation. And what he noticed is that if you start with an initial data in L2, then the solution gains 1 degree of regularity locally in spacetime. Okay? Now, on a technical level, how do you prove local smoothing? Well, one starts with a microscopic conservation law, namely the time derivative of a density plus the divergence of a current is equal to 0. And one integrates this against a switch function, such as the hyperbolic tangent. Now, when you take the time derivative of this object, the time derivative of rho becomes the divergence of a current. You take the spatial derivative and you move it onto the hyperbolic tangent in order to get this current, which is nicely localized by this function to a compact region of space, right? Now, what did Kato use for his density? He used the L2 norm. Okay, so in fact, his local smoothing effect is based on this microscopic conservation law of the momentum for the KdV equation. Now, our proof of local smoothing for the NLS and MKdV equation rely on the discovery of the fact that there is a microscopic conservation law that is underlying the macroscopic conservation of alpha. So what is this density? It's a function of the potential and the diagonal Green's function. And this density satisfies this microscopic conservation law where the current again depends on the potential and the diagonal Green's function. Incidentally, this gives us another proof of the conservation of alpha, because if one simply takes the time derivative of alpha over here, you get the time derivative of rho under the integral. So you get the integral of a divergence that is 0 for nice enough functions, okay? So our local smoothing effect works because it turns out that this current J over here is also coercive at the level of HS, all right? Now, the problem is that while local smoothing for NLS and MKdV are nice, they are completely useless for our discussion. Because remember, what we really want is a local smoothing effect for the difference flow. It is the difference flow over here that we want to show converges to the identity, okay? And here is the problem, right? So on one hand, we want to prove that the high frequencies under this evolution move sufficiently fast to give us a good local smoothing effect. And at the same time, we want to use this local smoothing effect to prove that this flow over here converges to the identity. So nothing much moves anyway, okay? So it's a very fine balance that needs to be struck, and one needs to rely on lots of cancellations in these equations in order to obtain a good local smoothing effect for this flow that then can be used to this flow to show that this flow over here converges to the identity, okay? So it takes us about 40 pages to make that happen, but we can make it happen. So at the end, what do we get? Here is the picture, right? We want to prove that the evolution under the difference flow converges to the identity in HS, but using local smoothing, we can only do this locally in space because that's what local smoothing gives us, and with loss of derivatives. We already know how to make up for the loss of derivatives using equicontinuity. So how are we going to get rid of the locality over here? How do we extend this to a global in space statement? One has to prove tightness for the solutions, okay? And tightness on the physical side is much, much more difficult than tightness on the Fourier side. And the reason why is because everything moves. Dispersion moves, solitons move, right? In fact, you can only hope to prove tightness of the orbits for compact time intervals, okay? So how do you prove tightness? You want to say that if there isn't much HS norm at the original time of spatial infinity, there won't be much HS norm over a compact time interval. So what do? You take an energy-like object and you integrate it against the cutoff, which is supported at spatial infinity. And you need to control the flow of energy through these transition regions in your cutoff. But this exactly involves norms of Q locally in space-time. So this is exactly what local smoothing is good for, okay? So by integrating this local smoothing effect into the commuting flow arguments that I described for KdV, one obtains well-posedness throughout the red regions, both for NLS and MKdV. Okay, so this is a joint result with Ben Harrop-Griffiths, who is a postdoc at UCLA, and Rowan Keller. So this brings me to my last topic and my very last two slides. Now, There are many reasons for which one would want to study an equation at low regularity, right? Obtaining the optimal well-posedness result for an equation can be a goal in itself, right? It completes the well-posedness picture. It ensures that we haven't missed any underlying instabilities in our equation. But there is another reason for studying these equations at low regularity, and that is that it brings us closer to studying these equations on the support of invariant measures, and so at thermal equilibrium. So rather than just saying things about the orbit of one solution, we can now say things about statistical ensembles of solutions. I'm running out of time, so let me just say the following thing. That it turns out that the methods that I discussed for proving global well-posedness for the KdV equation with data in H-1 also allow us to construct global dynamics on the support of the white noise measure, and proving that the white noise measure is left invariant under the KdV flow. Okay, and this was achieved in joint work with Rowan Kilev and Jason Murphy. So the image that you should have in mind is that of an infinite sea of solitons that have different velocities and different amplitudes, and that they are, bumping into one another, interacting. Okay. Now, in this joint work with Rowan and Jason, we construct global dynamics for such an initial configuration. Okay. Now, what distinguishes this infinite soup of solitons, right? The image you should have in mind is that of a pot that is boiling on the stove, right? What distinguishes this infinite soup of solitons from the case of H-1 data is that the infinite soup of solitons doesn't have any decay at infinity, okay? And yet the same tools allow us to construct global dynamics for H-1 data also allow us to construct global dynamics in this case, okay? So, right, in my opinion, this means that these tools are actually quite versatile, and I believe that they're going to allow for future progress in this direction. So I think I'm completely out of time. Thank you very much for your attention. I'm going to stop here.
Thank you, Monica, for the wonderful talk. And now I think it's time for the questions from the audience. So maybe Helena can help me in checking if I'm not missing any questions.
Sure. So far, no questions.
I have a curiosity, if I may. Can you please say something more about the periodic case? Because I didn't get, at one point I was convinced that the techniques could be extended also to the periodic case, but then you struck this impression and in one of the last slides. So what could you say for the periodic case?
So for the periodic case, right, the argument that I presented for the KdV equation does not care about the geometry. It works very well for NLS, for the periodic or the realigned case. So you can try to just run that argument in the context, let me find the slide, in the context of NLS and MKDV, okay? And if you do, right, the change of variables is going to be something similar. It's going to, right, instead of Q, we're going to look at this diagonal Green's function over here. And if you just employ exactly the same arguments, what we obtain is global well-posedness for NLS and MKDV all the way down to L2. Okay, so up to here. And we won't care about the geometry. Okay, this is going to work both on the realign and in the periodic setting. But you see, for NLS, this wouldn't give us any new result. It's true that this would be a new result for the MKDV equation, but it's not going to reach all the way down over here. Okay, so in order to cover the remaining red region over here, we need to start distinguishing between the periodic and the real-line setting, because we know that these results over here are sharp, right? This is a result by Bourgain for the NLS. It's a result by Capella and collaborators for the MKDV equation, and they all prove that it's sharp. You cannot extend it in the periodic setting in the red region. Okay, so if you want to make progress on the real line, okay, then you need to step away from the argument I described from KDV. You need an extra ingredient that distinguishes between the periodic setting and the real line setting. And we settled upon the local smoothing result as a tool that tells the difference, right? Because local smoothing works on the real line, but on the periodic setting, right? I mean, you just see the same high frequencies, just visit the same region over and over again. The local smoothing becomes some sort of averaging effect rather than a true local smoothing effect. Okay.
I see.
Right, and the same happens for other equations, right? So, for example, if you're willing to treat the derivative nonlinear Schrödinger equation on equal footing on the real line and the periodic setting, you can go all the way down to HS6, let's say. But if you want to go all the way to the critical regularity, which is L2 on the real line, you need to start doing something else, like using local smoothing. Okay. In the periodic setting, because we know that these equations are ill-posed, you need to start looking for renormalizations of the equations, right? For NLS, there is an obvious one, the weak-ordered NLS. So the right question to ask would be, can you prove that the weak-ordered NLS is well-posed? Can you somehow leverage this local smoothing effect that becomes a local averaging effect to say something about the weak-ordered NLS?
I see. Thank you. So there is one raised hand. I think Timur Akunov is correct.
I really enjoyed the talk and a variety of results put together. I had a question, and for other, so it seems that these techniques sort of adding classical dispersive things to the complete integrability sort of open new vistas in this completely integrable world. Other equations that you think this will be relatively routine, and others that it will be, really harder to imagine. Do you have some kind of judgment there?
So we're still talking about completely integrable models.
So these methods you seem to imply are primarily, at least using this mnemonic was particularly useful in the completely integrable world. And there are a lot of things on structure of completely integrable things, right?
No, that's a very good question, Timur. By the way, nice to see you again.
Likewise.
So, right now, it's not clear what these tools tell us about non-integrable systems, okay? But we shouldn't be so quick to dismiss them, right? I mean, if you think about it, right, how did the well-posedness in the green region work? One treated the nonlinearity as a perturbation of the underlying linear flow, which is completely integrable. So I'm not going to make any wild conjectures over here, but right, I mean, it's reasonable to expect that interesting results can be obtained by treating certain non-integrable models as perturbations of nonlinear, completely integrable models. Okay. Now, if you ask, what about these methods in the context of other completely integrable equations? Well, these structures vary a lot from equation to equation, right? So, for example, in order to prove local smoothing effects, one has to, from scratch, discover a microscopic conservation law like this, right? And if you do not discover this underlying microscopic conservation law, you're going to have a very hard time proving a local smoothing effect, okay? So the techniques are very much equation dependent. Whenever you start a new one, it's like starting from scratch. We have a guiding principle, you need to look at the renormalized perturbation determinant, but every single family is unhappy in its own way, sort of thing. Okay.
Okay. Any other questions? I don't seem to see other questions.
Raised hand.
There's one raised hand.
Raise a hand, yes.
Yes.
Yes, go ahead. I think Taj Munir. I don't know if you can unmute yourself and ask your
Yes.
question.
Oops. Okay. Ah, here.
It's not
No.
working.
Not working.
Yeah.
Here.
No.
If it's not working, you can always email me your question. I'll happily.
Okay.
Apparently he's unmuted.
He is unmuted, but I think there's some internet problem.
I think.
Email always works. So Taj, please email me your question and I'll answer.
Or in the chat also.
Not working. Okay.
Okay.
Any other question?
Okay. So there is a comment saying that the talk is fantastic.
Thank you, Taj. Yes.
Okay, he has a question about stability. I don't know if you can see it.
Okay, yes, I can see. I'm looking at the chat right now. I know typing is slower than asking, so be patient. Any region of stability. I'm not sure I understand that. Stability of what? Like orbital stability? Yeah, thank you, Michael.
Stability of the solution. Okay.
You mean beyond just saying that that the data to solution map is continuous? Stability under perturbations of the equation, perhaps. That would be indeed an interesting question, and it relates to what Timur was asking, right? If you add a forcing term to the equation that destroys complete integrability, can you say that solutions to the perturbed equation converge to the solution to the completely integrable equation? I think that's a very interesting problem and one that we have not looked at.
I think there was one more raised hand, but I cannot find it now. So messages to thank Monica.
Yes, thank you all for giving me an hour of your time. That's very, very nice.
Yeah, that was beautiful.
Thank you, Elena.
So Helena, what do you think? Helena, what do you think?
Thank you very much.
Yeah, I think we can wrap this up. Our speaker for next month will be Theo Drivas. Change
Yes.
subject a little bit.
So to answer a new question that came in, yes, there are
Oh.
results in the periodical case.
Oh,
So
okay.
for the KDV equation, the same argument gives us a new proof of well-posedness in H-1. This was obtained before. I didn't have a chance to say by Capella and Topalov, but this gives another proof that doesn't rely on inverse scattering techniques. And also this argument, right, whenever you can, whenever it works for the real line setting, you can make it work for the periodic setting as well, as long as you do not introduce this additional layer of local smoothing, okay? If you rely on local smoothing for the real line case, then you need to come up with new ways of integrating renormalization into this method of commuting flows. So this is actually something that we're looking at with one of the postdocs, right? Seeing how can one introduce renormalization techniques, say weak ordering, into this method in order to say something about the weak ordered analytics, for example. Okay. So by all means, yes, one can obtain result in the periodical case, but you can only go so far before you start hitting a new wall and new ideas are needed. Sure.
Great. So apparently there are no more questions. So maybe we can say thank you again to Monica for the wonderful talk.
Yeah, thank you. Thank you very much for giving me the opportunity to speak about this. Again, if there are any other questions and
I see. The last minute I was sure.
Hi, Gichang.
Oh, hi, Monica. Enjoy your talk very much.
Thank you very much.
Yeah.
Oh, it's wonderful to see you.
Yeah, thank you. Yeah.
It's been a really long time.
Oh, yeah, a long time. Yeah, last time we everything, right? We were...
Exactly, yes. Visiting Northwestern, very long time ago. So I was saying, if anybody else has any other questions, please email me and I'll get back to you as soon as I can.